Can people in the back hear me? Okay, great. We should get started. So a couple of announcements. So in the future, I mean, you guys are doing great, but I know sometimes like some students can come late, a little bit late. That's fine. Just remind your friends if they are late, when they come in, just be very quiet. So otherwise, it's hard for me to get started when people are constantly coming in, and that's very distracting. On the other hand, our class ends at 9:25, so really you shouldn't be packing your bag until 9:25, right? If you start to pack your bag before that, that's also quite distracting, right? That just like reminds me of like, oh, I should dismiss the class because students are, they want to leave. So please don't do that. If you have some emergency, you have to go. Do it quietly so it's not that distracting. Okay, so the last lecture we basically we started to talk about multi-component flash calculation. And we went through the calculation about the degrees of freedom, and the degrees of freedom is say plus 4, and then typically the composition and the fate, flow rate, temperature, and the pressure are given. So that leaves a degree of freedom 2. Now we talk about two simple examples, which is to use and then we simplified the whole set of equations, the mass balance, the energy balance, the equilibrium. We just condensed the whole equation into one, that's Rutherford equation, right? Then we talk about two simple examples, which is bubble point and dew point calculation. So in both cases, for example, if in both cases we know psi, right? Psi is here is mole fraction of vaporization, right? And because we know at the bubble point, there's no vapor, right? So psi is 0. At dew point, there's no liquid, so psi is 1. So we have 1. Then that gives us only 1 degree of freedom, right? Then we simplify the Rutherford-Rice equation to this form. Now, because there's only 1 degree of freedom, right? If we are given P, then we can find the T, right? That's the bubble temperature at this pressure, or other way around, right? So we talk about this. So today we're going to talk about isothermal flash, which is kind of a slightly more complex problem of how do we use Rutherford-Rice equation to do the to compute to calculate for a multi-component flash process. Well, in this case, for the isothermal flash process, the two given are temperature and pressure, right? It's kind of like we know the temperature and pressure we are operating the flash system at. And again, we know the composition of the feed, the flow rate, and the temperature and pressure. And so then based on the degrees of freedom analysis, we know that once temperature and pressure are given, there's no degree of freedom of the system, which means we should be able to solve for all the other unknowns. We should be able to solve for the composition in the liquid stream, vapor stream, the flow rate of the vapor, liquid, and as well as the duty on heat exchanger. So how do we do this? First, we're going to look at the example for an ideal mixture. For ideal mixture, typically here, the temperature and pressure we're operating at for the flash system is basically the same as a feed. Now, again, we can start from the Rack-Floyd-Rice equation. For ideal mixture, the key value, the key value is basically only dependent on pressure and temperature. It's not dependent on composition. And the model for computing the key value for a ideal system can be Raoult's law or the de Bruyster correlation. Now, because we know the temperature and pressure here, we can first determine the key value for each component, right? We can use Raoult's law, graphical techniques, or other models. Now let's look at this equation, right? Now we have key values, and they are compositions which are already known. And the only unknown here is psi, right? So we have one equation and we have one unknown. So theoretically speaking, we can solve this equation to get psi. And once we get psi, we can compute, the compositions and all the other unknowns. Now, this equation is kind of like a nonlinear equation. You cannot simply solve this equation to get psi. So that's why we need to use iteration method. And the way iteration works is that now we have key value, right? Once we know the temperature and pressure, we have a key value. The way the iteration works is that you make a guess about the value of the psi, right? You plug in the value of the psi into this equation, into the Rack-Floyd-Rice equation, right? Then you will get the value of this whole term. But that value is not necessarily zero, right? Because your initial guess might not be exactly the root of this equation. So there will be some residue. Now, based on that residue, you can make another guess, right? Just change your guess, get a new psi, plug into this equation, and do this iteration for many times until you get a psi value that's close enough. So we'll talk about what's the threshold to declare a victory about about solving this equation. Okay. So here's how to do it step by step. First, we choose a model for Ki, right? Then we can compute Ki based on the temperature and pressure. Then we can, once we have the Ki, then we can solve the Rack-Floyd-Rice equation to get psi, right? Once we get psi, we can compute this liquid stream composition with this equation here. We can also compute the vapor stream composition with this equation. That's here. Then we can also compute the vapor phase flow rate, right, based on psi and F, right? Because psi is defined as a ratio, the molar vaporization ratio. And then L, the liquid stream flow rate, is basically the difference between the feed and the vapor stream flow rate. Then we can also compute the duty on the heat exchanger. The way we do that is first we compute the enthalpy of each component at temperature T, right, which is given in this case, and then we can compute the enthalpy of your feed and your vapor phase and the liquid phase. Then you can compute the duty on the heat exchanger using the energy balance equation. Okay, that's for the ideal mixture. So it's kind of straightforward. For non-ideal mixture, it's a little bit more complicated. Now the difference is for non-ideal mixture, we know for ideal mixture, key value is only dependent on temperature and pressure, right? Then we can start one, and in this isothermal flash condition, temperature and pressure are given, so we can just compute the key value right away. Then we can, using this key value, we can start to solve. We can solve the rectifiable Rice equation to get psi, right? And now for non-ideal mixture, P value is not only a function of temperature and pressure, it's also a function of composition, right? X and Y. But at the beginning, we actually don't know the composition, right? So that's kind of we're kind of in a dilemma. We need to know K so that we can solve this equation to get psi, right? Then we can use psi to compute X and Y. But we don't know X and Y, so we cannot compute K, right? So for this problem, again, we have to use successive substitution as a method. And the idea to do this is, first you have to make a guess about key value, right? Now typically you can start from ideal system assumption, right? Just assume, start from ideal system assumption. Then, because temperature and pressure, you can still compute K, right? But this is gonna be only a guess. Then you can plug in this K into this equation and solve for psi. And with the psi value here, you can compute X and Y, right? Now you finish kind of the first step. Then you already have the Y value and X value, right? And you also know the temperature and pressure. Now you can calculate an updated key value, right? But now you have to use a model of key that considers not only temperature and pressure, but also the compositions, X and Y's. Now with this key value, you can update your value for psi, solve for psi by plugging Ki into this equation here. Now you get an updated value of psi, right? Then you can compare this updated value of psi with your initial guess of psi and see how different they are, right? If they are different, which means your solution hasn't converged yet, then you have to do this. Your solution hasn't converged yet, then you have to update Y and Xi using this psi value you just obtained from step 6, right? Then you can, you have to go back to step 3, calculate Y and Xi, and redo this whole iteration and get another updated psi value. So when do we know it's good timing? We can declare a victory. So basically, by doing this iterative process, you will get psi values, in every iteration. And here, if we look at this equation here, right? So basically, we can declare a victory when the psi value of 2 subsequent or consecutive iterations produce very close psi value, right? And the threshold for determining that is typically you can compute the relative difference between the psi value of your K+1 iteration and your psi value of your case iteration, right? And divided by the psi value of your case iteration. That's the relative difference. Whenever the relative difference is below 10 to the minus 4, that means you have achieved a very good convergence, right? Because in 2 consecutive iterations, your psi value is so close, the difference is even smaller than 10 raised to the minus 4. That means we have converged to a solution. There's another method to do this, which involves using the Newton's method. So this is the method given in your textbook. So in the Newton's method, and this method is kind of more the typical method used in process simulator, right? Because we're talking about a process here. If you're gonna work for a chemical company, you're gonna design a process. Most likely, you won't do it by hand, because in real case, the process is just too complicated to do it by hand. And there will be commercially available software that integrates all these equations we've talked about in our class, and you can just use the software to do that, to do the process design. But again, you have to understand the basics, and you have to understand how to set the parameters. So a Newton's method is kind of like a more common algorithm used to solve this problem. And we start from this, right? Now this is the Riceford-Rice equation, and it's a function of psi, right? And our goal is to find the psi value that satisfies and that make the whole equation here equal to 0, right? And again, this is a nonlinear equation, so you cannot solve it by simple method. And the idea of the Newton's method is you guess value for psi, right, between 0 and 1, right? That's the psi is the vaporization fraction, so it should be between 0 and 1. That's your initial guess. Then you can compute f psi, right? Just plug in psi here, compute this, you can get f psi. You can also compute its derivative, right? You can take this f psi with respect to psi, you can get f prime psi. And if you plug in the initial guess into the f prime psi, you can get its first derivative. Now you can use Newton's method to find the next guess, right? So this is the Newton's method's equation, right? So your k+1 iteration, the psi value for your k+1 iteration is basically the psi value of your kth iteration minus this, that's your f psi divided by its derivative. Now you have the second, you have an updated guess. So then you can ask yourself, does the guess converge, right? Does these two values, they satisfy the convergence condition we just talked about? If not, then we can go to step 2 and do this again, right? We can do step 2 again until we find with 2 consecutive psi value that converge. Okay. So typically, again, the convergence condition is met when the relative difference between 2 psi values is below 10 to the -4. Okay. Next, let's look at an example of using this method to solve a real example. So here, let's see, we have this flash process, and we feed this flash process with 100 mole per hour of feed consisting of 10, 20, 30, and 40 % of propane and butane and pentane and hexane, respectively. Okay, so these feed, they enter this destination column at this condition, right? 689.5 kilopascal, that's the pressure, and 366.5 Kelvin, that's the temperature. So assume, the mixture is in equilibrium, then what is the fraction of the feed coming out as the vapor, and what is the fraction coming out as liquid, and what are the composition for the vapor and the liquid? Okay. So now again, in this case, we can let's compare the conditions to see if they satisfy this scenario, right? Temperature and pressure are given here, right? And also the feed flow rate is given here. Feed composition is given here, and here the feed temperature and pressure is the same as the flash temperature and pressure. Okay. And now, if we assume ideal mixture, then we can find the key value for these 4 components, right? For propane, its key value is 4.2. For butane, it's 1.75, and etc. Okay. Now, to solve this problem, the first question we should ask ourselves is: at this flash condition is a fade, a liquid, a vapor, or two-phase, or it's a two-phase mixture, right? Because this problem only exists when we have, a two-phase mixture. They come out as two-phase mixture. Then we can use the method we just learned to solve for it. Right? So how do we do this? What we know is only the temperature and pressure of the flash drum, as well as from that we can get the key value of each of the component. So we kind of have to make a guess, right? We assume that this flash temperature is a bubble point, right? The flash temperature is 366.5 Kelvin. Then when we do that, because we know that from the bubble point calculation, we know if the system is at the bubble point, right, then psi is 0, right? So if we look at this equation, F0, that here psi equals 0, with plugging it should give us a value of 0, right? If it's not 0, that means our assumption is not correct. Then depending on how, the value of this term, we can evaluate if the flash temperature is higher than the bubble point or if it's lower than the bubble point. Okay. So here we can plug in the numbers. So we have the key values for each component, right? Just plugging it here. And also because now we're assuming the flash temperature is the bubble point. Then that means the flash is operated at the bubble point, meaning psi is 0, right? There's no psi is 0, there's no vapor. Plug in the numbers, and we get a value of minus 128. That's smaller than 0, right? That means the key value, I mean, it is negative, right? If this flash temperature is at bubble point, then we should get 0. But now it's negative. Negative means this key value is higher than the key value at the bubble point. Right? It's greater than the key value at the bubble point. So each term gives you a negative value, and you sum them together, that gives you a negative. Right? So that means the flash temperature is above the bubble point. Right? We can also do the same. So now the flash temperature is above the bubble point, right? So next thing we need to check is we want to know if the flash temperature is below the dew point, right? If the flash temperature is above the bubble point, meanwhile it's below the dew point, that means we are operating our system, in the two-phase region where we have vapor and a liquid phase both present, right? So now, next thing we do is we assume the flash temperature is at the dew point temperature. So here, again, you just plug in psi equals 1 into this equation, right? Plug in the numbers, you find out the value, we got a value of 0.72. That's larger than 0, right? Larger than 0 means the key value at this flash temperature is lower than the key value at the dew point, right? That means the flash temperature is below the dew point, right? Therefore, from this, to check, we find out we are operating at this flash drum at a temperature that's below the dew point, but above the bubble point. So we're operating, this stream is partially vaporized, right? So we will have a psi value that's between 0 and 1, right? So that's when we can start to use the Newton's method we just learned to do this computation. Okay. Now we can start from an initial guess of psi equals 0.5, right? That's a convenient way to start. In the first iteration, we start from the psi value of 0.5. Then you can plug in psi equals 0.5 into this equation. This is your Rachel Rice equation. You can get f psi, right? That's 0.25. And then you can also plug in psi into this equation that gives you the derivative of psi. That's this number, right? You can compute the next psi value by using Newton's method, right? This is the equation for the Newton's method that gives you this value. Then you can compute the relative difference between the k plus one, k plus one, the psi value in the k plus in this case, the psi value in the second iteration and the psi value in the first iteration. That gives you a difference, relative difference of 0.8, which is pretty big, right? Which means we're far away from convergence. Then we need to go to the next step, which is we start from this value, right? We use this value as the psi value for the second iteration, right? This is the same as this one. And we do the same, right? We compute f psi using this equation. We compute f prime psi using this equation. And we can compute psi k plus 1 using this equation. We compute the relative difference, right? Now, as we can see here, the relative difference basically decreased significantly from 0.8 to 0.2, but it's still much larger than the threshold, the convergence threshold we have determined. We can move on to do this again in the third iteration that further reduce this relative difference. Then in the fourth iteration, we find out, the relative difference is below 10 raised to the minus 4, right? That means within 4 iterations, we can get a psi value that's very close to the root of this equation, which is 0.1219. That means about 12.18% of the feed is vaporized as vapor, while the rest is leaving the flash drum as liquid in the liquid. Then we can compute the composition for the vapor phase and the liquid phase here, right? For the liquid phase, we can use this equation to compute the composition, right? Now we know the psi value, we know the k, we know zi. Just plug in the numbers, you can get the composition of the liquid stream. And using this equation, you can compute the composition in the vapor stream. Then this problem is solved. Any questions? So the next example we're going to look at is adiabatic flash, right? This is again slightly more difficult than the isothermal flash. In the isothermal flash, the convenience of the isothermal flash is the temperature and the pressure of the flash drum is given, right? So we can guess the key value. Then that will help us to start the iteration to solve for psi. But for the adiabatic flash, we don't know the temperature inside this flash drum. What we know is the duty on the heat exchanger is 0. Right? Still, we have these two conditions are given. Okay. Now we need to solve for composition, temperature, and vapor and liquid flow rate. So because the energy is the duty on the heat exchanger is 0, so that reminds of us the energy balance on the heat exchanger, right? Which is basically Q right now is 0. And then if you just substitute V by F multiplied by psi, L by F multiplied by 1 minus psi, you can just kind of reduce this equation to this form, right? Now this form is kind of a function of psi and the temperature, right? Because enthalpies are the function of temperatures. Now, instead of having only one equation to solve for the isothermal flash process, now we have 2 equations. We have the Rachel-Rice equation, right? In which this whole term psi is unknown, then we have an energy balance. Okay. So if in these two equations, right, if we know the psi, we can solve, if we know psi, then we can solve for xi, yi, the composition, and v and L. Then we can compute the enthalpies here, that we can compute this term. So how do we solve this equation? Now, instead of solving one equation compared to the isothermal flash condition, now we have to solve two equations. The way we solve it is, and first you choose a model for key, right? That's always, you need to do that. And this model of key will correlate your key value with your temperature, pressure, and composition, right? Otherwise, the linkage between K and the temperature is not clear, right? Once you specify a model, you have that. Then you can solve for these two equations to get psi and T, right? And you have to do this by iteration, right? And one way to do so is you guess a value of K. Well, basically, you guess a value of T, then you can get a value of K, right? Then you plug in K here, you can solve for psi. Then you get the psi, you plug in here, and you are examining the value of this equation and see how different it is from zero, right? If it's very different from zero, then you have to update your guess of T. And by doing this, iteratively, you will find out the value for psi and T, right? Then once you get the value of psi and T, you can calculate x, y, and the liquid, the vapor stream molar flow rate and the liquid stream molar flow rate, right? So do the iteration until the solution converges. Note at each iteration, we must update the values for the enthalpies, because we know the enthalpies is dependent on the temperature and the compositions. So in each iteration, once you have the value of T, X, I, and Y, you have to update them. Now, just to summarize, so far we talk about for the flash calculation, we've talked about these examples, right? First is about the calculation of the bubble point and the dew point, right? If you are given the temperature, how do you find out the bubble point pressure? If you are given pressure, how do you find out the bubble point temperature? And similar goes to the dew point and dew point pressure and dew point temperature calculation. So in these examples, we are able to simplify the Rutherford-Rice equation to this format, right? Then the way to solve these problems is basically, for example, let's take this as an example. We are trying to solve, given T, we are trying to solve P. What you do is make a guess about P and plug in the P value into this equation, right? Once you know P, you can know K. You plug into this equation, you compute the residue of this equation, right, between one and this term. And if this residue is not zero, then you need to update your value of P. And you do this by many iterations until you find a P value that really minimizes this residue to a threshold that you can accept. And the same goes to the other three examples. For the isotherm flash here, we know the temperature and pressure and the feed composition. We need to find out the psi and the composition. So we need to solve this Rutherford-Rice equation here, right? And again, here the way to solve it is you kind of like start from a gas of psi, plug in the gas here, you can compute the residue. And if the residue is not zero, then you update your value of psi until you find a psi value that minimizes residue. Newton's method is one kind of like very useful method to do this kind of iteration. So instead of artificially guess what is your next psi value. Newton's method will give you a psi value that will help you converge much quicker. Then for the adiabatic flash, we are given Q and P. We have to solve for psi, T, and X and Y. Now you have two equations you need to solve. And again, similarly, just make an initial guess about psi and T, plugging them here, and solve for the residue, and update for your guess until it converges. Okay. Any questions? So next, we're going to talk about ternary liquid-liquid system. And so far we're talking about basically gas-liquid equilibrium system, either binary, in which we have two components, or ternary, we have multi-component, we have more than two components. So next, we're going to talk about ternary liquid-liquid system using graphical method. So now let's look at this separation process here. We have a feed F that contains component A and B, right? And then we have a solvent stream S that contains a solvent C. While feeding these two streams into this unit, this separation unit. Now, if A is insoluble in solvent C, right? A is insoluble in C, then we'll end up in two streams. In a stream that's called a raffinate, we will still have component A and B, but in this case, the amount of B in this raffinate will be much lower than the feed, right? Because part of the B in the feed will be dissolved into this stream, which is called extract, will be dissolved into the solvent. That will form the extract stream, well, which contains B from the feed, and the C, that's the solvent. Okay. So for this problem, we can apply simple mass balance, right? Because if we know, the flow rate here, and we know the composition in the feed, and then basically the flow rate of the extract and the composition of the extract, the flow rate and the composition of the raffinate, they are constrained by the mass balance, right? In another case, if A is partially soluble in solvent C, things will get a little bit more complicated. In this case, because A is partially soluble in C, right? So when we mix, right, when this solvent stream and this feed stream mix in this separation unit, basically part of the A will dissolve in this stream, right? Because it's partially soluble. As a result, we will end up with a extract stream that has component A, B, and C, right? C is a solvent, then C will dissolve some A, and then because B is soluble in A, then B will come out together with A as well. So we will have extract stream contains A, B, and C. Okay. Meanwhile, we will have a raffinate stream contains A, B, and C. Right? The reason is if A is partially soluble in C, then vice versa, C is partially soluble in A. We will have some C being dissolved in the feed stream coming out as a raffinate. Right. Now this is a little bit more complex, and for this problem we won't do it by mass. Instead, we will examine the phase equilibrium and solve this problem graphically. Okay. So now let's look at the first example. So here we have carrier A is insoluble in solvent C. Okay. Now we can write down the mass balance equation, right? We have carrier A's moles balance, right? The incoming moles of carrier A is the mole fraction of A, XA, in the feed, right? the superscript parenthesis means the stream. Multiply the flow rate of the stream by XA multiplied by F of the feed stream. That will equals to, because now for carrier A, when it leaves the separation unit, it will only be present in the raffinate, right? So then if we know the mole fraction of A in the raffinate and multiply by the flow rate of the raffinate, right? These two should be equal, right? That's the mole balance for component A. So next, let's look at the mole balance of component B. For B, incoming stream, B is only contained in the incoming feed stream, right? It's not present in the solvent. But when the extract and raffinate leaving the separation unit, we have B present in both of them, right? Both in the extract and the raffinate. So similarly, this is the incoming moles of B, right? Which equals to the mole fraction of B in the feed multiplied by the flow rate of the feed. That equals to the mole fraction of B in the extract multiplied by the extract flow rate plus mole fraction of B in the raffinate, okay, multiplied by the raffinate flow rate. Okay, now we can do the same for the C as well. C is only present in the solvent stream and extract stream. It's not present in this stream, right? Because we are talking about a insoluble system, right? A and C is immiscible with each other. Then the incoming stream moles of solvent C is going to be equal to the mole fraction of C in the F extract multiplied by the the extract mole fraction. Okay. So here we're talking about mole balance here. You can also do this by mass balance, right? So basically it's the same. Now we can use AC balance to eliminate R and E in the B balance, right? Because now look at this. A and C, these two equations are kind of simple, right? And we can just convert. So let's look at how we do this. So if you look at this equation here, this is the balance for solute B, right? On the left hand side, it's not changed. On the right hand side, we can just substitute E, right? That's the flow rate of the extract by using this relationship, right? If you just divide XC XCE here to the left, then you will have E equals S divided by XCE, right? And you plug in that here, right? Then similarly, we can replace R by leveraging this equation, right? If you just divide XAR to the left, right? Then you have R equals this term divided by XAR, right? And you just plug in this term here. Okay. Now we have to make a definition here, right? So here we make a definition, FA equals XAF multiplied by F, right? So F is the total flow rate of the feed. XA is the mole fraction of A in the feed. And FA is basically the flow rate of A in the feed stream, right? Similarly, we can do the same for B. FB equals XB F, right? That's the mole fraction of B in the feed stream multiplied by the feed flow rate. That gives us the flow rate of B in the feed stream. Right? And the reason we do this is just to make this equation looks a little bit more neat. So then it will be convenient, as we will see later. Okay. Now let's also define this molar ratios of B to other component, right? Because we know that in the feed stream, we have both component A and B, right? We have both component A and B. And if we define capital B, so for any string, if we define capital B, right? Let's do this. So in the feed string, we have component A and B. In the extract string, we have component B and C. In the refinite, we have component A and B, right? If you look at these three streams, in each of these streams, we will have component B plus another component, right? Then we can just define capital B. For example, in the extract string, we can define capital B as the mole ratio of B in the extract string, right? That's XB, lowercase xb multiplied by the E, right? That's the flow rate in the extract string, divided by XA multiplied E. This is the mole flow rate of component C in the extract string, right? We define this. And then because E is common here, then it's denominated. Then XB, capital XBE is basically the ratio of the mole fraction of B divided by the mole fraction of C, right? So, I mean, at first it might look confusing, but this is just another way we can denote mole fraction of B, right? We want to simplify this equation to a more workable version. So we make this, and because in the fade string, the string, we all have the both component B and the other component. We can make this definition. Okay. Now with this definition, then we can just for example, we can just replace this term here. XB, lowercase xbe divided by lowercase xe. That's both in the extract string, right? And that's a molar fraction of B with respect to the molar fraction of C, right? And that's the definition of this, right? So we can just replace this ratio by uppercase XB. Okay. Then here we have in the refinite string, we have mole fraction of XB or of B divided by the mole fraction of A, right? That's the definition here, right? Which is just replace this ratio with uppercase XBR. Similar for here, right? For here, we need to replace F with, if we rearrange this equation, we divide XA to the left, then we have F equals FA divided by XAF, right? And you plug in this back here, you will have XB divided by XA, both in the fade string, right? That satisfies the definition of the uppercase XB. Okay. Now we simplify this equation to this functional form. So these are just algebra. So so if you cannot follow me, go back and read the lecture slides. It's not that complex. Okay. Now we have this equation, and we can make a definition here. We can define XBE by XBR as a so-called, this is like kind of like a partition coefficient, right? Because that means the mole ratio of B in the extract over the mole ratio of B in the refinite stream, right? And then we plug in the definition for capital XB and capital XBE and capital XBR. Well, that gives us this. Then we can further simplify this. Right? Okay. So here we have KdB defined. This is the real key value for a liquid stream, right? It's actually distribution coefficient for two liquids, and that's a ratio of molar ratio of XB in the extract over the molar ratio of B in the refinite. So this will be simplified to this. Okay. Now we can see this is only a kind of like a modified version of the distribution coefficient. Okay. Okay, I think we can stop here and we can continue in the next lecture.
It is not on Canvas anymore. Is that there?
So in exam 2, the last question turns out to be last problem turns out to be too difficult to solve, right? And so I didn't expect it's that difficult, right? So then, if that's the case, then you basically lose the function of distinguished students with different, capability. Now initially I decide to, just remove that problem from your grade. Then later I realized some students, even though they didn't really solve it in the exam, they did spend a lot of time in the exam solving that problem, right? Then we should give them, even though we should not punish students for not being able to solve that problem, then we should also not punish students because they spend too much time in solving that problem, they don't have enough time to solve other problems that they don't do well. Then I decided to still grade that problem, and then we'll add the point as bonus point in exam 2 for every student, right? And that's a difficult problem to grade, so it's going to take some time.
I really like it's so we can hold over again for the
Yeah, no problem.